So we now know that there are sort of two ways, at least we've discovered two ways of realizing some of the structure of the fundamental quandle of a knot, which we call Q of K. Right? One way of realizing it is by mapping it to what we call an Alexander quandle, lambda KT. The Alexander quandle, again, is this quandle whose elements are the elements of Z mod K, for some K, and with the triangle operation defined by the magic average mod K, TK, or sorry, TX, plus 1 minus TY. And so what this construction on the left does is it sets up one quandle homomorphism. In other words, this is a function which takes the fundamental quandle and associates with every element in the fundamental quandle, which is an arc in the knot diagram. It associates every arc in the fundamental quandle, A sub I. It associates it with a color, xi, which is an integer mod k. Right? And the various colors in the diagram for our knot are then related together by this magic average equation. Right? And so what we get, the image of the fundamental quandle over here, is what we call the Alexander module. And it's its structure, the structure of the Alexander module, that gives us the Alexander polynomial. It gives us the other elementary ideals that are associated with the matrix. So this is where we were living so far. It's where we got information about the Alexander polynomial from what's called the Alexander module, or the Alexander quandle, which is this lambda kt object. So that's one viewpoint that we have. The other thing that the Alexander module in our setup, we were required to see the difference between the orientations of various crossings. So x triangle y was defined in this way for the magic average, but if we had an inverse crossing, x inverse triangle y was, according to the work that you just did over here on the backboard, defined by the same kind of equation with the t inverse replacing the t. Right? T inverse here, y. And all of that came from the following observation. Right? When you discovered this invertibility formula for the magic average, what you really ended up showing is that x triangle y, triangle inverse y, let's actually work this out for a second to verify that this actually does what we think it will do for this particular type of realization of the quandle operation. So this, let me put some parentheses in because it's not associative. X triangle y is going to be tx plus 1 minus ty. If I triangle inverse that with y, then that's going to give me, oh boy, I'm going to run out of space pretty quickly here. T times, no, it's going to give me T inverse, because I'm doing the inverse triangle here. T inverse times Tx plus 1 minus Ty plus 1 minus T inverse times Y. Now I'm doing that thing that we always hate when our students do, or our algebra work is starting to crawl up the side of the page because we ran out of space down at the bottom. Oh well. We all know how to read this. You're not having to grade this paper, so we'll let it slide. So if we actually do out the arithmetic on this, then what I get by distributing this T inverse over here is going to be T inverse times Tx, which is just x, plus 1 minus T times T inverse. That's going to give me T inverse minus 1, I hope, y. And then over here, I have 1 minus T inverse, y. But lo and behold, T inverse minus 1 and 1 minus T inverse are opposites of one another. So if I distributed this y, I would get coefficients of T inverse minus T inverse plus 1 minus 1. Both of those terms cancel, and we're left with just plain x. So that work that you just did on the backboard to demonstrate the invertibility for this magic average operation showed us exactly this, right? That we can undo a triangling by y by just using an inverse triangle by y on the right? That it just undoes whatever that triangling by y does and leaves us with just x back again. So that was super important in Quandle land. And we saw when we were working on the Alexander polynomial for the figure 8 that we really did have to be careful about positive crossings versus negative crossings, because if we weren't, then we wouldn't get T inverse in the right place where we need a T inverse and T's in the right place where we need T's. And that satisfies for us the most general definition for what it means for the Quandle operation to be invertible. But I wanted to take a few minutes for us to explore the question of, well, what if we didn't see the difference between positive crossings and inverse crossings? What if there were no orientation on our knots? So let's take a dive into that for a few minutes, going back to our trefoil. If we think about the trefoil as an oriented knot, I'm going to call the three arcs in my diagram, instead of using x1, x2, x3, I'm just going to call them x, y, and z, just for simplicity. So x is going to be this first arc, y is going to be my second arc down here, oriented now in this direction, and then z is going to be the arc out here, oriented in this direction. And so if we think of the trefoil as an oriented knot and then ask the question, well, what kinds of elements are in its fundamental quandle? Well, the fundamental quandle is generated by the arcs. So x, y, and z are going to be elements in that quandle. But then it's also generated by the triangles of all of those various, every other element, basically, that's in here. So x triangle y is going to be an element. X triangle z is going to be an element. Y triangle z is going to be an element. And then we're also going to get elements like x triangle y, triangle x, and x triangle y, and so forth, and so forth. X triangle y, triangle z, and so forth, and so forth, and so forth. Right? So there's going to be a whole ton of elements that make up this fundamental quandle. Some of these elements we can understand better by looking at the knot diagram. So for example, at this northernmost crossing up here, x is crossing underneath z and becoming y, and that crossing ends up being an inverse crossing. Here I am driving my car under the bridge. The traffic is going from my right to my left over the bridge. So this is an inverse crossing. So in particular, this crossing is going to tell me that y is equal to x inverse crossing z. So I suppose we can replace y in this y triangle z element here. I can replace the y with x inverse triangle z. Right. When I do that, what do I end up with? I end up with inverse triangle z and then triangle z. Those are going to cancel and give me just plain x. So I find out that y triangle z is not a new element in my fundamental quandle. It's one of the same elements I've already written down. It's just the arc x. Let's see if that should that be a surprise. I don't think so, because if we look at this crossing over here, this is a crossing in which z crosses under y at an inverse crossing and becomes x. So x is equal to z inverse crossing y. And somehow that's, in this diagram at least, the same as y crossed under z. But notice that there's actually, were it not for this observation, there's no place where y is an inbound arc that crosses under z at a positive crossing. So without this observation, we wouldn't have known how to simplify this, this element. Similarly, for x triangle y, we don't have a positive crossing of x under y. We only have a negative crossing. So if we want to understand what this is, we should probably, again, try to find some other relationship between x, y, and z that we can use to try to simplify. But in principle, as long as we're seeing the differences between positive and negative crossings, we might, if we had a more complicated knot, we might get stuck with the wrong kind of element in my quandle, where I have maybe x triangle y, and I don't have a way to simplify that, but I do have a way to simplify x inverse triangle y, or vice versa, right? So not seeing that difference can make our life more complicated. Seeing the difference between positive and negative crossings can make our life more complicated. So what if we had just not seen that difference at all? If we willfully blind ourselves to the difference between positive and negative crossings. And there may be a million reasons to do that because it's kind of annoying to work with orientations. But if we did that, suddenly our life is going to get considerably simpler because now y is no longer x inverse triangle z, it's just x triangle z, right? Because now there's no difference between positive and negative crossings. Y is the same as x triangle z. So then this element, just becomes the same as y to begin with. X triangle y becomes the same as so if y is the bridge and x is the under arc, that means I must be at this crossing right here. Here's x under, y the bridge becomes z. X triangle y becomes the same thing as z. Y triangle z becomes the same thing as x. Same story. So it turns out that if we, for the trefoil at least, if we don't distinguish between positive and negative crossings, every single element of my fundamental quandle simplifies completely into one of the three arcs. That's going to simplify into z triangle x. That becomes y. And so forth and so forth and so forth. And so what we get in that case is something that, instead of calling it a quandle, we call it a different kind of structure. It's a particular, again, a particular type of quandle. We call it a key, or a K. I actually don't remember how this gets pronounced. I'm going to go with K. So this gets called a K. And what a K is it's first and foremost, it's a quandle, right? So it's still going to satisfy all the quandle operations. Except the invertibility criterion now gets replaced because we're no longer going to see the difference between a positive crossing and an inverse crossing. We no longer have a separate inverse operation to the original quandle operation, but we declare the quandle operation to be its own inverse. So this is a new type of invertibility. We might call it self-invertibility. Self-invertibility. That just says for all x and y, we have x triangle y is equal to x. Maybe put parentheses around this first. X triangle y. Right. So same as this, except with replacing the inverse triangle with just another triangle. Self-invertibility, I just realized, has a better name in mathematics. I should probably use that word. Close. We call this involutory or involutary. The triangle operation is an involution. So sometimes we speak of a K as being an involutory quandle. It just means that it's a quandle whose quandle operation undoes itself on the nose. So we don't have to have a different way of inverting. We just use the same operation twice, and we've inverted itself. So what that means is that Ks are generally simpler than quandles, because we don't have to keep track separately of inverse triangle stuff versus positive triangle stuff, because everything can always undo itself. So in the case of the trefoil, we can simplify all these elements in the fundamental quandle. Once we no longer see orientation, every element in the fundamental quandle can be simplified down into just x, y, or z. And that's super handy, right? Because the fundamental quandle of the trefoil is ginormous. The fundamental K of the trefoil is just x, y, and z. And, moreover, we can understand the whole structure of the fundamental K of the trefoil just by creating this little operation table that can tell us what everything triangle, everything else is going to be. Right? In particular, what is x triangle y going to be according to what we did? X triangle y is z, because x, y, and z meet at a crossing. For the same reason, y triangle z is x, and z triangle x is What's x triangle x going to be? X. That's rule number 1 for Quandles, which is the same as rule number 1 for Keis. Y triangle y for the same reason. Z triangle z for the same reason. And then what about x triangle z? It's going to be y. How do we know that? Yeah, just...
You need to have one of each.
We need to have one of each. That's not obvious. It's true, but it's not obvious. So why do we need to have one of each here? Or maybe going more specifically to the point, why is x triangle z equal to y? Where do I have a crossing where z is the bridge and x is one of the underarcs?
That one right now. Oh, yeah.
Right, this one right here. So for the same reason that y is equal to x triangle z, x triangle z is equal to y at this crossing gives me that remaining y that we didn't have in that row. Y triangle x, so x is the bridge, y is an underarc. That is right here, right? X is the bridge, y is one of my underarcs, so y triangle x is going to give me z. And z triangle y is going to give me x. So what happens is, once we no longer see orientation, this crossing at which we can define y in terms of x and z, we can also in the same way define x in terms of z and y, right? Y triangle z is equal to x at this crossing as well. Whereas if I were in Quandle land with an oriented knot, in order to solve this equation and get this one, we would have had to use an inverse triangle of z on both sides to do that. But here, to solve this equation and get the x by itself, all I would have to do is triangle by z on both sides, regular triangle. And on this right-hand side, I'm going to get x triangle z, which according to the involutory property is just going to be x. And then y triangle z on the left-hand side. So as soon as we no longer have a difference between the positive and the backwards triangle, it makes the whole structure of the quandle much simpler. Right? And so we associate this object called a K. I have to get that right. Associate a K to this. And the fundamental K for the trefoil is finite. It only has these 3 elements, and we can completely draw out its entire operation table. And we get an operation for every single pair of arcs for the trefoil, because it turns out that every pair of arcs in this diagram does actually meet at some crossing. So we can always come up with the full table. So inspired by that, so the work that you did to find the Alexander polynomial of this was all done by treating the figure 8 as an oriented knot, right? And so you built a presentation matrix for its fundamental quandle, and then use that to discover the Alexander polynomial. If we ignore the orientation on this, now the 4 arcs, let's say I call my 4 arcs W, X, Y, and Z. Let's say. So maybe this one's W, this one we'll call X, this one here Y, and then Z over here. You can imagine that your operation table for the K of the figure 8 we know, based on the properties of any quandle operation, what the diagonal on this is going to be, right? And we can infer, based on some of the crossings in this diagram, that, for example, Y triangle W is going to be Z. Right? So that fills in an entry right here. But the question that you're going to have to reckon with in this process is, what is, oh gosh, hold on. Now, maybe this one is not as bad. Because every pair of arcs in this diagram is going to meet at least one crossing, if I'm not mistaken, right? X meets Y here. X meets Z there, X meets W also there. Right? And I think the same is true for the others. So maybe the figure 8 is not, I mean, definitely this is an exercise worth doing. But you can imagine that in a diagram with more arcs in it, like 6-2, for example, there can be a pair of arcs that don't actually meet at a crossing in your diagram. And for those, we are going to get new elements even in the fundamental K for arcs that don't actually meet at a crossing in common. Right, so it does matter in principle, right, which is the overcrossing and which is the undercrossing. So X triangle W, this would be where X is crossing underneath W is the overcrossing. And so this one, we don't know, right, because there's no crossing where X goes underneath W. On the other hand, there is a place where W is going underneath X. In particular, W goes underneath X and turns into Z. So if I want to know what X triangle W is, then is there a way to infer that from this equation? So what if I triangle with W? Well,
so you triangle with W on both sides?
If I triangle by W on both sides on the left, so if I do this, I'll find out that X should be W triangle Z. Let's double check that. X equals W triangle Z. Is that true? Does W cross under Z and become X? It looks like W doesn't actually cross under Z.
W
crosses over Z, right? But this must be true, right? According to our observation from a moment ago, the observation that W triangle X is equal to Z, right? If this is true, then doing W triangle, hold on. Because the non-associativity is going to screw us up. If we try and triangle stuff on the left, we don't necessarily get what we want. Because this W triangle X is going to get stuck. It's stuck together. So if I try to triangle on the left, I'm not necessarily going to be able to simplify what I have here. Because I don't have the associativity which would be required to slide the parentheses out and make this any simpler. So what this must mean then is that X triangle W, or W, X triangle W. X triangle W must be, even though it's something we can create with our operation, it's not one of the arcs in this diagram. It's an element in the fundamental K, but it's not an arc. And so it's got to be a separate part of our operation table. So I would just include X triangle W as a new thing. We could give it a name if we wanted to. You call it A or something like that. Maybe I'll do that just for simplicity. If I call that A, then it means that I'm going to have an A here. And that means that I should have an A as part of my operation table for this K also. And then go in and figure out how A interacts with the other arcs. And so we might have some more calculations to do. So it may be that the fundamental K, instead of having 4 elements for this, might have, how many elements can we imagine now? Maybe there's 8, maybe there's 16. And so maybe this table is big, but hopefully at least it's still finite. Ideally, this is still a finite fundamental K. And it turns out that there are, in fact, infinitely many knots that have a finite fundamental K. So it's not completely a fool's errand. We can understand a lot of different knots by using finite fundamental Ks. But in general, we might have a lot of work to do to spell them all out. But I do think it's worth trying. One of the things I'd like for you to try is to make some more progress in this program of figuring out what all needs to go into the fundamental K for the figure 8. If it is finite, then what does that operation table look like?